Hello and welcome back. I'm Professor Hendricks and I'd like to talk to you about different operators that are relevant now that we've talked about composite data types like lists and dictionaries and whatnot. The first one I want to talk about is, the is operator. So let's see an example. So if I were to create a variable x is equal to 500 and another variable y is equal to 500, these two have the same value but they are not the same variable. And we can see that by typing x is y and confirm that they refer to two different things. The reason for that is because every single data type, every single variable has an ID associated with it. I can find the ID of a variable by typing ID of x and ID of y and confirm that they have different IDs. Now, however, in the case of ints, it's funny that I started with ints. There's something weird about ints, and that is if I were to say something like x is equal to 5 and y is equal to 5, and then also try x certainly has the same value as y, but check x is y. It turns out they refer to the same variable, and I can refer to this using the ID function again and confirm that indeed these have the same ID. The reason for this weird behavior is variables from -5 to 256 are pre-stored in a list in Python, and it's actually accessing those predefined variables, and that's why they have the same ID, because the value of 5 was sort of already preloaded into Python, I guess, with some designated ID. But in the example before where I did 500, that was outside that range from -5 to 256, so it created a new variable that has a new different ID. Let's see this example in the case of lists where it could potentially be more relevant. So I'm going to define a list L1, and I'll define it as 1, 2, 3, just for simplicity, and L2 I'll define it in the exact same way. And then I'll ask, is L1 have the same value? Whoops, of itself, certainly, and of L2, yes, of course. And what about is? Turns out this is false because these two lists have a different ID, and you can confirm that with the ID function. But what if I were to make a copy of a list? So let's just say if I made a copy, L3 is equal to L2, and then I ask, is L2 does it have the same ID? And it turns out it does. And the reason for this is because when you make a copy of a list by just using the equal sign on its own, it actually doesn't create a separate data structure or a separate object. So in other words, if I type L2 and L3, and if I were to modify L3, for example, changing the value indexed by 1 and making that 793, and then I check out L2, and it was also changed along with L3. So that confirms that these two variables, L2 and L3, in fact refer to the same underlying data structure behind the scenes. And we can confirm that with the ID function. So if we try L2 and L3, they have the same ID, but if we check L1, it was a different ID because we created it differently and we didn't create it as a copy of the other ones or make the other ones from it as a copy of it. So the way we get around this is by making what's called a list copy or a deep copy. So in this example, if I refer to define L2, and I could make a copy of that by using list of L2. And so what that means is I get another list that has the same contents, but if I check if they're the same object, it is false. So this deep copy essentially goes through and copies element by element, makes a copy of each component to create a brand new composite data type, a list. Now, another important operator that I wanted to mention is in, and that also directly relates to lists and other composite data types. So now that we have composite data types, they're sort of like multiple data types in one. So for example, if I have L3, I can definitely say if 1 is in L3. And indeed, it is. And if I were to check some other number like 2 is in L3, it is not, but it is in L1 because if you recall, L1 was defined to be 1, 2, 3. And so because we modified the variable indexed by 1, in this case the value of 2, in the L3 case, and replace it with 793, 2 is no longer there. But if we try 793, is that in L3? Of course it is. It's that particular element. So the in function allows us to check if a particular component, like an int, float, string, or whatever, is part of another composite data type like list, dictionary, tuple, or set. Now, another use of in could be in the context of strings. So for example, if I just define a string, if I were to define some DNA sequence, and then I want to see, is the CG dimer, is CG in DNA? And it is indeed in there, it's right here. Basically, you can use it to check whether or not a particular substring is in a larger string, and that substring can be arbitrarily long, can even be the entire sequence itself. Another important operator that I think we should discuss now is sort of different from the other ones, and that is a modifying operator. And so that is not. So not can be used along with these other operators to negate them. And so not is sort of like a negation operator. So for example, I could say CG not in DNA. And that is false because CG, as we pointed out, is in fact not in that DNA sequence. But I could also check some other larger sequence to confirm that it is not in that sequence. So not can modify in. And in this instance, the not comes before in, similar to how you might speak it or say it in ordinary English. And another example of where not can be used is along with the is operator. So for example, you could say L1 is not L2. That is true. And L3 is not L2 is also true because we did that list copy earlier. So, but if I made a copy and said L3 is equal to L2, then that would change and become false because so the not operator acts as you might expect given how English works and how you might expect it as a negation operator and how a negation operator would behave to do the opposite of the original operator. With that, I'll close this video on these extra operators that are very relevant to composite data types, and I'll see you next time.